So I'm going to dry off this piece in which I want you to hold. There's mineral oil. What do you notice about the mass of that?
It's really light.
Yeah, real light, in which you have your lithium batteries, lithium-ion batteries. One big advantage is that you have less mass per mole of electrons. So did you get that? So if I cut some of this off, now we've got a fresh cut. And what do you notice about the lithium? Lithium's a metal, isn't it? And so we have the lithium, the metal look to it. What I'm going to do is to put in some phenolphthalein into each of these beakers. When did you use phenolphthalein?
For titrating.
Good. So your group 1 metals, what are they called?
Alkali.
Why do they call them alkali metals?
Because they're a base.
Because they react with water to produce a basic solution. Their oxides react with water to produce basic solutions. So the color change you are going to see is because of that nature, that basic nature. Morgan, you want to tap it into that first beaker, please? So what do we notice about the reaction?
It's pretty violent. Not too bad.
You see the bubbles coming off? What are those bubbles?
Hydrogen?
Yeah. So lithium is losing electrons going to the lithium ion, the water, the hydrogen in the water gaining electrons to go to hydrogen gas. And what we want to compare is this rate of reaction. So as we go from on the board from lithium, sodium, potassium, what happens to the size of the atom?
It gets larger.
It gets larger. I'm going to go ahead and put this back in here. And then we'll take a look at sometimes if you get too big of a chunk, now it can pop out, and so now you would have molten lithium or molten sodium flying through the air at some poor person. So here's a chunk of sodium. Now, you see it has an oxide coating on it. And as we cut the sodium metal, we want to look quickly at the metal luster of it, but it ends up, it's going to fade quickly because of reacting with the oxygen in the atmosphere. If we slice off a piece, we can see the metal luster. It is a metal, but it kind of loses its luster quickly. So, Parker, why don't you toss that in the next beaker? You notice that it is a sphere. So that's molten sodium already, in which from the temperature, it ends up, it's melted and it's just scooting around on the surface. Scooting around on a cushion of hydrogen gas as it's reacting with water to produce hydrogen gas and sodium hydroxide. What can we see about the reactivity from lithium to sodium?
It's more violent.
A little more reactive, and we'd expect if we go down the column that we would see that reactivity increasing.
Doesn't that look like something you could buy? I would drink that.
I can drink this too.
Needs vodka.
here is a piece of potassium. It kind of feels like Play-Doh. It's soft. Your metallic bonding depends on the number of valence electrons. So your group 1 metals, they have few valence electrons, and so they're kind of squishy. And you see that if you hold it for any length of time, it will start feeling warmer and warmer, so that it can be reacting with the moisture on your skin, just like it would react with the moisture in the beaker. But they're very soft metals, and so as your number of valence electrons increase, number of valence electrons increase, your metallic bonding increases. So if I cut it, you see that you've got your metal luster, but here even more quickly it fades. And so here, Ben, why don't you toss this in the next one?
Bro,
He does
why
it.
did you do that?
See, what do we see about the reactivity?
It's a lot more
A
reactive.
lot more reactive.
Why'd you make me do that?
I don't want to get hurt. But,
You're a great guinea pig.
but as we went from lithium to sodium to potassium, what do you notice about the increased rate of reaction? Okay, why?
Because of their size.
Okay, so as the size increases, what happens to your ionization energy?
It gets less.
Okay, it decreases, gets less. So it takes less energy for that electron to come off, so your reaction rate's going to be quicker. What do you notice about potassium and copper on the 4th row of the periodic table? You see that they're what? About 10 apart, 10 atomic numbers apart. So what happens to the size as you go from the left to the right in the periodic table?
It gets smaller.
It gets smaller. So on the board, you see that the copper and potassium both have a 4s1 electron that if they were to react would be lost. But we see with copper in water, and we use it for copper water pipes, right, that potassium and copper both have a 4s1 electron. But why is the copper not reacting? What about its size?
It's smaller.
Smaller size, and the ionization energy
Is higher.
is higher, and so now it takes too much energy to pull that same electron from the 4s1 because your nuclear charge increased. You have 29 protons versus potassium with 19 protons, and those electrons